Hello, everyone, and welcome to today's webinar, Scattergraph Principles and Practice. This is part 3 of a multi-part webinar series. In today's session, we will cover sanitary sewer overflows and combined sewer overflows. My name is Eric Lott. I'm the marketing manager here at ADS, and I'll be serving as your host today. As always, we really appreciate you joining us for today's webinar. Today's speaker is Kevin Enfinger. Kevin is a product manager at ADS with 25 years of experience in environmental engineering and consulting. He's worked as a project manager, project engineer, region engineer, and most recently as a product manager for us here at ADS. Kevin is a registered professional engineer in 6 states, a member of the American Society of Civil Engineers and the Water Environment Federation. He has authored numerous technical papers and presented numerous presentations through these organizations to advance the science of wastewater collection systems evaluation. So thank you, Kevin, for your ongoing contribution to our industry, and especially today for the time and effort in preparing the information for this webinar. So without any further introduction, Kevin, we'll turn it over to you.
Thank you, Eric. It's good to have you guys with us today. I appreciate everyone who has joined in for the webinar. And I think many of you have been with us for the part 1 and part 2 of this webinar series. And so I appreciate having you back for part 3. So we're going to learn some interesting things today about sanitary sewer and combined sewer overflows. Now, just an overview about this webinar series. The purpose of this series is really for us to learn how to use scattergraphs of flow monitor data. And particularly, I'm talking about the depth and the velocity data from area velocity flow monitors to understand the various flow conditions that we observe in what I call the urban sewer environment. And there's really, with each webinar, there's 2 questions I want us to focus on. And that's, what do these scattergraphs tell us? And just as important, or perhaps even more important, is what are the implications that these scattergraphs imply? So there's a lot that can be learned about these particular graphs and looking at this type of data in this particular way. And I know at ADS we've learned a lot about these over the years. We've incorporated a lot of these findings into our regular operations and the regular insight that we provide to our customers. And I find it very useful when others learn how to use these tools as well. Very powerful. So let's talk about sanitary sewer overflows first. So a sanitary sewer overflow, or an SSO, is a discharge of untreated wastewater from a sanitary sewer system. And obviously that's a bad thing. Causes for these include inadequate sewer design or construction, insufficient operation and maintenance, power failures, or even vandalism. So they have a variety of causes. And the impacts are often compounded by infiltration and inflow in the system, which can contribute to an increase in SSO duration, volume, and or frequency. So I know a lot of times we don't tend to see the SSOs until wet weather, or at least the really big ones. And a lot of times there's a tendency to blame the overflow on inflow and infiltration or wet weather in your system. Oftentimes, the telltale sign, the telltale cause that triggered the event was actually some type of other downstream restriction or capacity limitation. And it was the I&I that just kind of was the straw that broke the camel's back, if you will. And one of the things I want to introduce you to today is what I call a prelude to an SSO. So we talked about various factors that can cause an SSO. But I find that in general, regardless of the contributing factors, sewers often experience a common sequence of hydraulic events prior to an SSO. And they include uniform flow, backwater, and surcharge conditions in that order. We talked about some of this in the part 2 webinar, where we learned how to evaluate these different types of conditions. And I'm showing here a profile drawing of these 3 different conditions in a sewer. And if you recall from the part 1 and part 2 webinars, one of the things that I mentioned is if you can learn to recognize patterns in a scattergraph and then immediately identify them with a profile view, as I'm showing here, of a sewer, the physical meaning of that data on the scatter graph becomes much more apparent and much more readily accessible to you. And so these are three patterns that you will see develop over and over and over prior to overflow events. We're going to look at various examples of those today. So this is a side profile view. Let's take a look at what the prelude to an SSO looks like in a scatter graph. And these are using some of the tools that I've discussed in the past two webinars, including the Manning's equation to describe uniform flow and ISOQs to help us identify backwater conditions. So here I'm showing you data from an 18-inch circular sewer. This one happens to be in Tennessee. It's an example we showed before. And adding the Manning equation to this particular scatter graph allows us to see data that follows uniform flow conditions. And then you can see and infer what's happening in the rest of the data set where the data does not agree with the Manning equation. And in effect, that helps us define the three conditions that are going on in this data set. Below half pipe, or 9 inches and below, we are pretty much looking at uniform flow conditions. Above that, the depth is actually deeper and slower than you anticipate, but the pipe is not yet surcharged. So between 9 inches and 18 inches, we have a sewer here that's in backwater conditions. That means the capacity is being limited by something downstream. Eventually, because of that limitation, this pipe surcharges, and you can see this one surcharges all the way to a depth of nearly 72 inches. So there we have uniform flow, backwater, and surcharge, and those are the prelude conditions to an SSO. Because if that sewer continues to get deeper, what's going to happen? You're going to have an overflow at some point. It's going to be either at the monitoring point, it could be downstream further, or it could be upstream of the monitoring point. So let's take a look at several of those examples and how they manifest themselves in a scatter graph. So here is a profile drawing showing a sanitary sewer overflow upstream from a monitoring location. So you can see where the flow monitor is positioned in the upstream pipe in the center manhole on this graphic in front of you. Flow is moving left to right, and you'll notice that the low elevation manhole is upstream. So as this pipe fills up, it happens to overflow at the lowest elevation manhole, which in this case is upstream from the flow monitor. So let's take a look at what that looks like in a scatter graph. So here's data from a 42-inch diameter sewer. This one happens to be in Maryland. And again, by now you should already recognize that this location has uniform flow, backwater, and surcharge conditions in it. And we've learned today that those are the prelude conditions to an SSO. So we see the uniform flow conditions denoted by those data points that agree with the Manning equation. So up to 21 inches, or again, half full in this pipe, we see uniform flow conditions. Above that, we have backwater conditions, and we go into surcharge up to about 126 inches in this particular pipe. So we can mark those conditions off as well. You should be getting very good at identifying those conditions in these examples now. We can also use ISOQs to see what flow rates things are happening at. So you can see in this particular sewer, our minimum flow depths are cruising along at about 8 million gallons per day. The design capacity, or the projected capacity on this pipe, is about 57 million gallons if you were to use the capacity based on the Manning equation. But the pipe, or the capacity, or the operating capacity at which this site reaches at full pipe in reality is only about 33 million gallons per day. And you can see as it surcharges, it pretty much stays about that flow rate. Now, the SSO in this case is indicated by this grouping of data points at the top of this surcharge data. And that is a classic signature right there of an upstream SSO. Now, why do we have that pattern? Well, if you think about it, the monitor is measuring the flow that comes past it. However, when you have an upstream SSO, the same amount of flow continues to come past the monitor, but the additional flow starts leaving upstream before it ever passes through the monitor. However, that upstream manhole is a controlling elevation, if you will, at the overflow point, and therefore we will see the depth kind of bounce around a little bit around this the static depth at which the overflow is occurring. So you will see data points over time. The longer that SSO happens, the longer you'll see data points cluster in this little area at the top of the scattergraph. And that is a classic signature of an upstream SSO. Now let's take a look at a sanitary sewer overflow from a monitor or from a manhole that is downstream from a monitoring location. So in this case, you'll see the low elevation manhole is actually downstream of the flow monitor, and that's the location, if surcharged high enough, that this particular stretch of sewer is going to overflow. So what does that look like in a scattergraph? So here's an example of a 30-inch sewer. This one comes from California. And again, you can probably already pick out three hydraulic regimes of uniform flow, backwater, and surcharge that are the prelude to an SSO. The Manning equation helps us figure that out, and we can mark those on this scattergraph. Now, just like with the upstream SSO, a downstream SSO is characterized by what happens at the top of the surcharge data. And what you see here is actually the depth reaching a depth of about 65 inches. And you'll notice I've also added ISOQs to this graph. And you can see this pipe surcharges at about 10.5 million gallons per day according to the ISOQ line. But once it hits an elevation around 65 inches, the velocity actually starts to increase. And it increases to a maximum velocity that's associated with another ISOQ at 13.3 million gallons per day. And this is the classic signature of a downstream SSO. And what happens here is in a downstream SSO, remember the monitor is measuring all the flow that comes through it. And that capacity, in this case, gets throttled to 10.5 million gallons per day until the overflow goes active. Then additional flow is able to leave the sewer system. That allows additional flow to come through the monitoring point, and that flow actually gets measured. So that's why we see the velocity go up. But since the depth is controlled by the downstream SSO, the depth remains constant or relatively constant. So classic example of a downstream SSO from a monitor location. Now here's another twist on the downstream SSO. This is a sanitary sewer overflow from what I call an overflow pipe. Sometimes I affectionately refer to this as a poor man's combined sewer overflow. In some sanitary sewer systems, particularly some of the older ones, if they've had problems in the past with basement flooding or something like that, in some areas it was a common practice to go in and find a convenient manhole where you could knock a hole in the manhole and put a pipe out to the creek or to the nearest receiving body, or in some cases the storm sewer system. I've seen a number of these over the years, and of course these are not allowed under current regulations, and a lot of cities that have had these in the past, they've either eliminated them or they are in the process of eliminating them. But here's what they look like in sewer data. So if you ever see something like this, it's one of the items to look for is an overflow pipe in a downstream manhole. So here's an example of a 10-inch diameter sewer. You see the data here, and we are going to plot the Manning equation on this scattergraph. And that denotes three regions that you have in this data. You have uniform flow, backwater, and surcharge conditions. But you'll notice the surcharge conditions look a bit different than they did in the previous example. So once you get up to about 22, 24 inches or so, you notice the velocity start to increase and the depth starts to increase as well. And so the question is, what's happening here? We can plot ISOQ lines on the scattergraph as well and see the flow rates at which these occur. So you can see here the operating capacity of this pipe is 0.43 million gallons per day. And the anticipated capacity of this pipe is 1.06, which we do ultimately achieve, just not at full pipe. We achieve it at a much higher depth in surcharge conditions. So what's causing this is actually an overflow pipe in a downstream manhole. And you can see I've plotted that overflow pipe at the appropriate elevation and with the appropriate diameter. And you can see basically as soon as the depth rises to the invert of the overflow pipe, that allows flow to start to escape the system in an additional place. And that allows the velocity to go up and more flow to come past the flow meter that's in the main sewer line and get measured as an SSO. Now, along the lines related to upstream and downstream SSOs, I wanted to touch on a related topic of reverse flow. There are often times that we are asked to set our flow monitors in a bidirectional velocity mode where it can measure flow velocity in both directions, depending on what actually is observed. And what I can tell you is that reverse velocity in sewers is actually a pretty rare phenomenon. And there's been very few cases where I've been able to document it conclusively. But I want to show you one example of where it has happened and it was confirmed and what it looks like. So I'm showing you a profile drawing of a sewer with reverse flow. And to have reverse flow, you have to have your elevations in your manholes such that they're driving flow in the reverse direction. If you don't have that, you can't have reverse flow. But this is what it would look like and what it should look like. Let's look at a data example. So here's data from a 12-inch sewer. You'll notice this scattergraph looks a little bit different. And at first glance, you think, my goodness, those velocities are awfully offset to the right. But if you look at the velocity axis, what you'll see is that there are some negative velocities plotted on this scattergraph. And that some of my velocities up the very, very top of this scattergraph are actually negative velocities. So what do we really have here? Well, I can plot the Manning equation, in this case using the Stevens-Schutzbach curve, the Stevens-Schutzbach method, and that allows me to project what the capacity of this pipe should be based on the data we measured. From that, we have what we call a dead dog in the sewer using the Stevens-Schutzbach method, which tells us that all of our data below full pipe is actually some form of backwater condition. And then above that, we go into surcharge conditions. Now, we can plot some ISOQ lines on here. And these look a little bit different than you've seen before because this is the first time I'm showing you negative flow rates. So you can see anything along the zero velocity, any depth at zero velocity is zero flow. That's why you have a vertical line there that represents the zero flow ISOQ line. The positive flow rates above that look like typical ISOQ lines. The ones that are negative, they look like the ones on the positive side. They're just flipped around the other way. But this allows us to see what's happening here. So this sewer, day in and day out, below, say half pipe, it's operating pretty much as we would expect it to. It gets a little more full and it goes into backwater conditions. So this is perhaps during a rain event. It surcharges, and you'll notice that as it continues to rise in depth, in a surcharge condition, the velocity then starts to get slower. So it's rising deeper, but the flow in the sewer is moving slower and slower and slower until at about a depth of 72 inches, it just stops. But it only does that momentarily because it starts going in the other direction. And you'll see that the depth continues to rise, but the flow is now in a negative direction. This example actually occurred, as I mentioned before, in a 12-inch sewer. But this 12-inch sewer is located in a place where it's coming into a much larger sewer. And that larger sewer and the conditions within it at some point start to dictate the flow in this 12-inch pipe. So the much larger downstream pipe, if you will, becomes a bully to this 12-inch pipe, and it forces flow in the other direction. This could result in an SSO in this 12-inch sewer somewhere upstream if the depth gets high enough that a low elevation manhole is achieved. Didn't happen in this case, but it could happen under a more severe rainfall event. So that is a good example of what reverse flow looks like in this particular application. Let's take a look at some combined sewer overflows now. So combined sewer overflows are a little bit different from SSOs, and they are discharges of untreated wastewater from a combined sewer system. I guess in some cases they are partially treated depending on what kind of structure you have around them. But basically it's diluted wastewater with stormwater mixed in. It's being discharged before it gets to the treatment plant, the regular treatment plant. So combined sewer overflows generally occur during wet weather events. That's when they're designed to occur, and they do so when the combined flow rate of wastewater and stormwater exceeds a certain capacity. Anything above that capacity then goes out as a combined sewer overflow. So CSOs occur at regulators that are designed or adapted for this purpose, and they usually incorporate some type of weir to facilitate discharge to a receiving water body. So I'm going to show you two examples of combined sewer overflow regulators. The first one here happens to be what I refer to as an end weir. I'm showing you a schematic graphic that shows you how an end weir operates. So flow is moving left to right in this particular graphic. So the flow comes into the structure from the left, and typically during dry weather, it gets diverted to the right and goes out a smaller pipe to the wastewater treatment plant. In wet weather events, if the flow gets high enough, it will actually flow over a weir wall and then go directly to the receiving water body, a river in this case. Let's look at an example of one of these in a scatter graph. So here is flow monitor data from a 30-inch diameter sewer. This one happens to be in Ohio. And you can see we have an interesting looking pattern. This really doesn't look like any other thing we've seen so far in the first two webinars. It doesn't really look like anything we've seen in terms of an SSO, because everything here is happening before this pipe ever gets full. So I can use the Manning equation to define parts of this data. And in this case, I've used the Stevens-Schutzbach method. And I have a little bit of a dead dog here, not much of one. So you could actually probably argue that the data set that passes through this Manning equation is a little bit of backwater, but for all intents and purposes, you could call it uniform flow. But above about 5 inches, you go into a more extreme form of backwater. And then at about 12 inches or so, you'll notice the velocity starts to increase again. So right about here, you can see my arrow on the screen. And above that, we can see that the velocity goes back up. What's happening here? We can look at this with some ISO2 lines, and I can see that this backwater pattern here occurs at a depth or a flow rate of about 0.5 million gallons per day. And we have that flow rate until about 12 inches, and then when the velocity kicks back up, you notice we go all the way up to 3.7 million gallons per day. So something is allowing extra water to move through this sewer pipe and through this monitor. Well, it turns out it is the CSO overflow structure. So in this case, this 30-inch diameter sewer is routing flow through a CSO regulator into a 15-inch diameter sewer that heads to the wastewater treatment plant. And there is a weir. The weir height is set at about 12 or 13 inches, and you can see that agrees right here with where that velocity kicks up. Every bit of this flow right here is flow that is going over the weir out to a CSO discharge point. That's a good example right there of a combined sewer overflow over an end weir. Let's look at another common example. This is a CSO over a side weir. So again, flow is left to right in this graphic. Most of the time, during dry weather, normal flow conditions, flow comes in from the left. It goes into a CSO regulating structure and gets funneled into a smaller diameter pipe going to the wastewater plant. However, in higher depths, typically during a rainfall event, the water goes over the side weir and out to the river. So let's take a look at an example of this. So here's data from a 120-inch diameter sewer. This one happens to be somewhere in Indiana. And you'll notice that we have a little, most of the data operates down near 20 inches or below. And then you see something else that is happening above that. So right in this range, it's a little different. What is this? How do we take a look at it? Well, I've actually went back and got the design parameters on this particular monitoring location, and I drew a Manning curve using the design method. So I've taken the design slope and assumed the roughness coefficient, and I show that this data never agrees with this design curve. And that tells me that this pipe does not operate under uniform flow conditions. So we operate in backwater conditions at all times. I can also plot some ISOQ lines on here to look at what's going on. And you'll notice that I see an inflection happening in this data right here at 13 million gallons per day at roughly 30 inches or so. That's where my overflow across the side weir starts. You can see my velocity goes rapidly up, and that at maximum depth, maximum velocity, I actually hit a flow rate of 100 million gallons per day. It doesn't look like that because we haven't seen flow rates like that in other examples before. But I want to remind you, this is a 120-inch diameter pipe. This is a big pipe with a lot of flow and a lot of flow capability. If you were to expand this design curve all the way out to full pipe, this pipe is actually capable of carrying, from a design standpoint, 239 million gallons per day. So we get a clearer picture of the side weir in operation when we overlay some additional elements about the CSO regulator. So I mentioned this is a 120-inch diameter sewer funneling flow down into a 54-inch diameter sewer. But long before that pipe gets full, we actually start to overflow over a side weir that's at roughly 30 inches. And you can see when that happens, you get the increase in velocity. So sometimes understanding how these structures operate, or at least having a good idea of what type of structure you're dealing with, can help you interpret the data. Or you can go the other way with these, and you can use the data and your knowledge of the structure to actually compute the overflow duration and volume from these in this manner. So we're going to talk about that a little bit. That is actually one of the biggest benefits you can get, not only identifying these events when they occur, but to use and leverage that information to help get you more accurate estimates of the duration and volume of these overflows when they happen. So here's an example we're going to use and kind of walk through. And this is a 12-inch diameter sewer, and you can see that it goes into backwater and surcharge, and we have identified a downstream SSO in the data. Got some ISO cues that are marking that information, and there's a couple of terms that I want to introduce you to that we're going to use to help figure out the overflow duration and volume. One is what I call the flow depth at the onset of overflow, D sub 0. The other is what I call the flow rate at the onset of overflow, Q sub 0. Now keep in mind, this data comes from a monitor that is just upstream of this monitoring point in this case. So this flow rate is what's going through the pipe, not out the overflow pipe, but through the pipe at the time the overflow starts to happen. And basically anything above that we're going to assume is what's going out the manhole or the overflow structure as an overflow. Doesn't work in every case, but in this case of the downstream SSO, this is a very good assumption to make. So how do we do this? So the first part is the overflow duration. And this is calculated by determining the number of recorded flow monitor measurements where the depth exceeds the depth at the onset of the overflow. And if you know that the sample period between each of these measurements, you can simply multiply that out and come up with the duration. So oftentimes the monitoring work that we do at ADS, we are taking measurements every 5 or 15 minutes. So that sample period will govern how much time you allot to the flow rates measured at each of these increments to help you determine overflow duration and volume. Now, the overflow volume is calculated as shown here. And yes, I am showing 3 equations. I don't want anybody to get scared about equations here. They're not that frightening. But the first thing that we do is we calculate the overflow rate, or the overflow flow rate at each time step in our data. And we do that by calculating once the onset of overflow depth has been exceeded, for every point or every time stamp that meets that condition, we then take that measured flow rate at that time step and we subtract out the flow rate at the onset of overflow. That gives us the information we then need to calculate the volume that occurs within that time step, the overflow volume. And then we sum each of those time steps up, each of those volumes for each of those time steps, and we come up with the total overflow volume. Sounds a little complicated, but it's actually not. Something can be done very easily in a spreadsheet. You can take all 3 of those equations and consolidate them down into one, and it looks something like this. So very easy to follow. So here's an example of how you run the numbers on something like this. So the example that I showed you in the scattergraph just a couple of slides before, I'm actually showing you data from that particular graph. And you can see we have 2 groupings of columns here. The columns highlighted in blue on the left, this is data that comes out of your flow monitor. So I've got the date and timestamp, I've got the depth, the velocity, and the associated flow rate at each timestamp. And you'll notice that in the we got the 1, 2, 3, 4, 5th row here at 1800 hours or 6 p.m. This is the first time that my actual recorded depth exceeds my depth at the onset of overflow. So for that example, we define the onset of overflow at 80 inches, and or actually 81 inches. You can see this is the first number that gets above that. All of these subsequent numbers are just above that and indicate that an overflow is active. Now, once I have that information, then I can do these additional calculations that are highlighted in green. And these are the overflow calculations. These are done separate and apart from the flow data. The first thing I do is I calculate the overflow rate at each time step. And all I'm doing here is taking this measured flow rate and I'm subtracting out the flow rate at the onset of overflow. And I can tell you for this example, the flow rate at the onset of overflow was equal to 0.82 million gallons per day. That's why in this first row of the overflow, you see we take 0.822 minus 0.82, and that gives us 0.002 million gallons per day of overflow flow rate for that time step. We convert that to gallons per minute, multiply it by the 15-minute sample rate we have here, and that gives us 25 gallons that occurred during that 15-minute time span. We do this for every time step. I don't have enough room to show you the entire event, but I'll jump to the end of the event. And you can see here that the overflow ends the next day at 2 a.m. when the depth drops back below 80 inches. And you'll notice our overflow calculations go back to 0. But we take all of these values here, we've been calculating, we sum them up, and we get about 20,000 gallons that occurred during that overflow event. So not only can we calculate the duration, but we can also calculate the volume of that event. And typically when I'm running numbers like these, I will report the volume estimate to the nearest 1,000 gallons. Now, that's an example of how to do those calculations. I also want to talk about some of the limitations involved. So the calculation procedures we've just talked about are really best applied to SSOs that are located downstream from a flow monitor when you have backwater conditions that are experienced prior to the overflow event. In other words, you need those prelude conditions to really get a good fix on when those conditions occur. You can also do this for some of your CSO calculations as well. The one place you really can't do this method is for the upstream SSOs. And the reason why is that additional flow that leaves the SSO does not come through our monitor, and therefore it's not measured. So we can use the scattergraph techniques to help us identify the elevations at which the upstream SSOs occur and hence the durations, but we cannot use it to estimate the volume of overflow for an upstream SSO. Just keep those limitations in mind. So a few key points to remember regarding scattergraphs and SSOs and CSOs. One is that sewers often experience a common sequence of hydraulic events prior to an overflow. So these include uniform flow, backwater, and surcharge conditions. And I think by now you guys are pros at identifying those conditions on a scattergraph. From there, overflows are readily identified by evaluating flow monitor data on a scattergraph. You look for that telltale pattern at the top end of the data, the top end depth-wise, and that'll help you identify overflows both upstream and downstream from a monitoring location, including SSOs and CSOs downstream. From there, we talked about some methodology to estimate the duration and volume of SSOs and CSOs. Those can be used for downstream overflows based on the flow monitor data, but we did talk about some limitations that they are subject to as well. Now, we did cover a lot of material today on SSOs and CSOs. All of this information is captured in a technical paper that Pat Stevens and I wrote a number of years ago. So that reference to that paper is here. It's also available for download on our ADS website, adsenv.com. So if you'd like additional details or an additional look at this information, please go grab a copy of that paper and take a look. It's very well described in that paper. In previous webinars, we've also talked about our Scattergraph Principles and Practice poster. So today's webinar actually covered the entire third row of that poster. The first webinar we did on fundamentals of scattergraphs covered the first row of the poster. Second webinar we did 2 weeks ago on backwater and surcharge conditions and the introduction of isoquantity curves actually covered the entire second row of this poster. That poster, if you would like, is available for you again, you can go to our website, adsenv.com/scattergraph, and you can download a high-res PDF of that poster for your use. And then that brings us to the next part in this series. Part 4 is something called pump stations, siphons, valves, and other structures. Or in other words, it's my version of planes, trains, and automobiles. But basically, we're going to talk about how to look at nearby structures near your sewer lines and start to make interpretations about how those structures are performing based on what you're seeing the behavior in the sewer nearby do. So this can be convenient when you're upstream of a pump station. There's also some valuable insights you can get about the performance of siphons. And then we'll talk about some valves and some other curious findings. We do have some other parts planned that are coming up after that. So part 5, 6, and 7 are also on some other interesting topics. And with that, Eric, I think we will turn it over for questions.
Thank you, Kevin, and thanks to everybody on the call today who has submitted questions over the duration of this webinar series. Kevin, the first question is, how far away can a sanitary sewer overflow or combined sewer overflow be to see its signature in a scattergraph?
Yeah, so this question was submitted by one of our webinar attendees up in Pennsylvania, and it's actually a fairly common question that we get. So it's a very good question, and I would say that the answer is it depends. So it's really a function of the configuration of the sewers in a particular area. So sewers with a mild slope often allow you to see further downstream than sewers with a steep slope, as the backwater effects often propagate further upstream. So when you're trying to better understand an overflow in a known location, it's best to position the monitor as close to it as you can. That's what I've found out. However, it's very hard for me to give you an exact answer on how far downstream you can see. Is it on the order of miles? No. Is it on the order of several manhole reaches? Absolutely. But how far within there depends really on the slope of the sewer. So my good friend Hadam El-Sai, he works for Barge Solutions out of Atlanta. He and I have actually debated this topic a number of times, and I think he's actually on the webinar today. And we've actually discussed plans for how to kind of test this theory out using some hydraulic modeling to take a sewer with a known configuration and then start to adjust it in the model to see how far or how less far you could see an overflow. And it's some interesting work. We haven't gotten around to moving forward on that, but I'm hoping that we can do some of that. But that's the answer to that. Is you can see downstream, but how far is very difficult to answer.
Okay, question number 2. Can you use a scattergraph to identify a hole in the sewer, such as a hole in the invert or a hole in the sidewall?
Yeah, so that's another interesting question. And in general, I would say probably not. But let's kind of talk through this or kind of think about it for a minute. So if we're talking about a hole in the sewer with no infiltration or exfiltration, the hole would actually have to cause some type of obstruction in the flow that then might become visible in the scattergraph. So in other words, you've got to have some disturbance to make it visible in to change the hydraulics. So for example, a hole in the invert, it might show up as a dead dog if part of the pipe protrudes into the flow or if debris starts to accumulate there. So there could be some indicators like that. Likewise, a hole in the sidewall of the pipe, maybe that might show up as a new source of backwater when flow exceeds a certain value. If we think of the other option, if a hole results in a significant amount of infiltration or exfiltration, that's something that we might detect as an emerging increase or decrease in flow rate. Again, these are possibilities that might be seen, but I suspect they would be difficult to see.
Okay, this next question. I have seen interesting scattergraph patterns in flow monitor data when the flow monitor is located upstream from a combined sewer overflow regulator. Any insight?
So yes, indeed. There's a lot of insight that comes from being upstream from a CSO regulator. So in this webinar today, we've shown two specific examples of combined sewer overflow regulators. So one that I showed was equipped with an end weir, and one was equipped with a side weir. However, there's almost an endless variety of these CSO regulator configurations. And because of that, you'll often see some very interesting things happening in the scattergraph data. And this kind of reminds me of a commercial that's on TV. It's one of the farmers insurance commercials where there's an actor that says, "We know a thing or two because we've seen a thing or two." And so at ADS, we've worked on hundreds of these CSO structures throughout the U.S. and Canada over the years. And one of the things that we've learned from that is that if you take the monitor data and you take the good measurements during installation of how that structure works, you know, what is the depth of the overflow? Do you confirm that depth at the top of the weir? The size of the pipes that are involved, those types of things. And you combine all that information, then those interesting patterns that you see in the data, they start to make a lot more sense. And I think you saw that in some of the examples we looked at today, where if you're just looking at the scattergraph by itself with no knowledge of the regulator, you kind of have to guess a little bit as to what's happening. But once you start to see the details of the nearby regulator, then the data starts to make a lot more sense, and you can start to state with a lot more confidence how that regulator structure is behaving and whether or not it's behaving as intended or in a slightly different manner.
Okay, this next question is actually two parts. The first question is, why not just measure combined sewer overflows in the overflow pipe? And the second part of this question is, why do you prefer to measure upstream of the overflow instead?
Okay, that's a very good question, and it's also one that we hear quite often, and so I wanted to be able to address that here today. So the answer is that we've arrived at that position after quite a few years of experience. So while the overflow pipe seems like an intuitive place to monitor, it's often a poor choice hydraulically. So one, you have overflow pipes that can experience long periods where they're completely dry. And that means there's no means to verify that the sensor is functioning properly between overflow events. So that can be challenging. Two, the overflow pipes can experience long periods of stagnant flow. So you can imagine like river intrusion or tidal intrusion that can lead to silt and debris problems on the sensors. Three, the actual hydraulic conditions in the overflow pipe during an overflow event are often chaotic, and they can be problematic for accurate measurement. So these pipes rarely have the conditions that most of us would deem to be acceptable or preferable to obtain high-quality flow measurements. So the next thought that most people have is, well, if the overflow pipe is not a good location, how about using a depth sensor at the weir wall along with a weir equation? And so this approach actually can work in some situations, but there are three potential pitfalls that you need to evaluate. So one, do the approach conditions to the weir satisfy the approach conditions required by the weir equation? A lot of times we are guilty of using weir equations without making sure that they're valid for use under conditions that we're trying to use them. So I caution you to look at the approach conditions and do they satisfy those required of that equation? Two, do the discharge conditions over the weir satisfy requirements of the weir equation? That's another part that gets people in trouble sometimes. And then 3, do you expect the tide, the river or lake elevations to exceed your weir height periodically? And I've actually seen that where one location in the southeastern U.S., the river, under some extreme flooding conditions, was backing up over the weir at a CSO structure. And the crew that managed that location and did the regulatory reporting, they were actually reporting some insanely high numbers for that structure during these events, because they were just taking the depth over the weir, plugging it into their equation, and using the number that was spit out without thinking about the implications of what was happening there. And the numbers they were providing were just wildly overstated. So you have to take that into consideration. If you've got any type of backwater or backup condition over your weir that's giving you a submerged weir condition, your weir equation is toast. So placing the flow monitor just upstream from the CSO regulator, we have found over the years often produces the most trusted results. So the examples we've shown you today are fairly straightforward from the 2 CSO examples. However, as the complexity of the structure increases, some additional sensors may actually be required to help with that monitor just upstream. So sometimes we will measure the elevations of the tide or the river on the outlet side of the structure. And sometimes we'll actually install inclinometers on flap gates or bending weirs to help us best determine the operational status of those for a particular regulator. In fact, those more involved examples may lead us to an additional webinar if you guys are interested, particularly those in the Midwest or the Northeast where you guys have more overflow CSO structures. So if you're interested in that, let us know, and we'll see about putting that together.
Okay, we'll make that our last question today. Of course, we'd love to continue to receive your questions related to scattergraphs. So if you have a question or if you'd like additional information on what Kevin covered today, please email me. Thank you very much for your attendance today, and this will conclude today's webinar.